2 days ago, a telescope perched in Chile turned its gaze toward one of the most thoroughly examined patches of sky in astronomical history, a region researchers have been poring over since 2003, and it still managed to turn up something brand new. Quick note before we dive in. Subscribe now, because this is the very first genuine science output from an instrument that's going to repeat this feat every single night for the next decade. Before going further into this new release, it's worth pausing to understand the observatory itself and the story behind its name, since that background explains why this milestone carries so much weight for the people who spent years working toward it. The telescope sits atop Cerro Pachon, high in the Chilean Andes, chosen for its dry air and dark, largely cloud-free skies, perfect for catching faint light from deep space. It bears the name of Vera Rubin, an American astronomer who decades ago studied the rotation of galaxies and noticed something odd stars in the outer regions were moving far too fast to be explained by the visible matter alone. That finding became one of the strongest pieces of early evidence for dark matter, an invisible substance believed to make up a huge portion of the universe's mass despite never having been directly observed. The observatory built in her honor was designed to keep pursuing answers to the very question her work first raised. The mission it carries out is called the Legacy Survey of Space and Time LSST. After capturing its first test images in June 2025 and following months of calibration and system checks, officials confirmed the real survey officially began on June 30th, 2026. Željko Ivezic, who heads LSST, explained that the green light came only after a thorough operational review of image quality survey, speed system reliability, and calibration accuracy, because once that 10-year clock starts, there's no quietly correcting small errors along the way. Even before the official start, the observatory had been sending out roughly 100,000 automated alerts every night since February 2026, flagging anything in the sky that had moved, brightened, dimmed, or otherwise changed. Those early alerts already helped confirm new supernovae and contributed to identifying more than 11,000 previously uncatalogued objects in our own solar system, all before the primary mission had formally begun. Officials expect that once the survey hits full speed, the nightly alert count could climb into the millions, backed by a global network of automated systems and follow-up telescopes ready to respond the moment something unusual appears, the Cosmos Field Release. Here's why the timing matters. On July 31st, 2026, the Vera C, Rubin Observatory released a new image of a region called the Cosmos Field, short for the Cosmic Evolution Survey. This wasn't just another image. It was Rubin's first official LSST camera image and catalog release, built specifically for real scientific use, an event the observatory is calling Early Data Preview 2, EDP2. Everything shown publicly before this, including the images from 2025, came from a long commissioning and calibration process meant to confirm every part of the telescope was functioning properly ahead of the real 10-year survey. This Cosmos Field release is different. It's built from genuine science validation observations gathered between April 2025 and January 2026, marking the observatory's first real step into ongoing scientific data collection and public release. Why choose the Cosmos Field for this milestone? Out of every patch of sky imaginable, this one located in the constellation. Sextans isn't some obscure region picked for convenience. It's among the most heavily studied areas of the observable universe, the Hubble space. The telescope stared at this exact spot from 2003 to 2005, and in the years since, it's become something like a scientific benchmark thanks to the sheer volume of data various telescopes and teams have gathered there. Before Rubin ever pointed its camera that way, astronomers had already cataloged more than 2 million individual galaxies in the Cosmos Field. Using earlier surveys, researchers picked this region because it can be studied from both the ground and space, and because so many prior independent observations of the same patch give scientists a reliable way to check whether Rubin's new data lines up with existing knowledge. Put simply, before pointing Rubin at entirely uncharted regions, scientists first aimed it at the one place in the sky they already understood better than almost anywhere else, specifically to confirm the new instrument works as intended. And it clearly does. What's in the image? The new Cosmos Field image was assembled by stacking hundreds of individual exposures from the observatory's LSST camera, the same 2-gigapixel camera that remains the largest digital camera ever built, years in development specifically to make an achievement like this possible. Packed into the combined image are more than 500,000 individual galaxies and over 5,000 stars. Within that massive population, astronomers can already spot enormous variety: delicate spiral galaxies with sweeping arms, smooth elliptical galaxies, chaotic galaxies mid-merger, and extremely faint, extremely red galaxies from some of the most distant reaches of the observable universe, because the cosmos field happens to contain relatively few bright foreground stars. From our own Milky Way astronomers get an unusually clear view into deep space uncluttered by nearby stars, letting this single image showcase a wide and representative range of distant galaxy types, the scale of it. Here's where the size of this achievement really comes into focus. This cosmos field image is just a small sample of a much larger data release. Alongside it, Rubin's EDP-2 gives the scientific community a full deep stacked view covering 3,000 square degrees of night sky, roughly 1/6 of the entire visible southern hemisphere, all from observations taken before the 10-year survey had even properly started. And this is only the beginning. Now that the primary mission is underway, the observatory captures around 700 high-resolution images every night, steadily working across the entire visible southern sky, before circling back to do it all again just a few nights later, comparing to the first public image. It's worth comparing this release to Rubin's first widely publicized image nicknamed the Cosmic Treasure Chest, released during the original First Look event in June 2025. That image focused on the southern region of the Virgo cluster, the nearest large galaxy grouping to our own about 55 million light-years away. It combined 185 exposures captured over 7 nights and revealed roughly 10 million galaxies within a 15 square degree patch of sky. At the time, scientists noted that even 10 million galaxies represented only about 0.005 of the roughly 20 billion galaxies Rubin expects to eventually capture over its full 10-year survey. That earlier image was spectacular, but it was still fundamentally a demonstration, a proof of concept from the commissioning phase before the full scientific pipeline calibration systems and cataloging software had been validated for publishable science. The Cosmos Field release is a different kind of milestone the moment Rubin's actual data processing system, the software that turns raw captured light into a verified structured, searchable catalog, professional astronomers can build research on, was formally proven to work, a global open project. All the raw data Rubin captures travels from the Chilean mountaintop to a U.S. facility hosted at the Department of Energy's SLAC National Accelerator Laboratory, where it becomes available to the broader scientific community. One key group working with this data is the Dark Energy Science Collaboration researchers spread across dozens of institutions worldwide tasked with using Rubin's observations to precisely measure how fast the universe is expanding and how matter is distributed throughout it. Scientists have pointed out that this marks the first time in astronomy's history that this much high-quality observational data will be made available to so many researchers. At once, astronomers won't need specialized equipment or their own supercomputers. They'll simply log into the Rubin Science platform through a standard web browser, meaning a researcher at a small underfunded university has essentially the same access as one at a major institution. Over the full 10 years, the observatory is expected to generate roughly half an exabyte of data, an amount so vast that engineering teams have spent years building automated algorithms to detect, measure, and catalog every astronomical object without requiring manual review. The sheer speed of it. Each exposure from the LSST camera covers a patch of sky equal to about 45 full moons side by side, and the camera captures a new exposure roughly every 40 seconds throughout the night. Multiply that across a decade of continuous operation, and it becomes clear why officials say Rubin is expected to gather more astronomical data in its first year alone than every other optical telescope on Earth has collected across the entire history of astronomy. Combined, not close to that total. Greater than it, by a wide margin. That's not an incremental upgrade over previous telescopes. It's an entirely different category of instrument. The machine itself, the LSST camera, sits atop Rubin's 8 4-meter primary mirror mounted on the Simony Survey telescope. Its imaging sensor is built from 189 individual CCD chips arranged into one unified array capable of capturing 3,200 megapixels per exposure. The camera weighs around 3,000 kilos, about 6,600 lbs, close to the size of a small car. It's a remarkable feat of engineering given the precision required to keep something that massive perfectly stable and focused, while capturing extremely faint distant light. Why Rubin is different. Most large telescopes focus narrowly staring at one small patch of sky for a long time to gather as much light as possible from a single target. Rubin does the opposite, built for speed and coverage, capturing huge sections of sky quickly, then returning to the same spot again and again over days, months, and years. Across its full 10-year run, Rubin will revisit every region of its visible sky roughly 800 separate times. That repeated revisiting is what lets Rubin build something almost no other telescope can, a continuously updating time-lapse of the changing universe rather than a single static photograph. This combination of wide, fast coverage and deep repeated observation is exactly what made Cosmos such a fitting choice for this milestone, giving the science team a region where Rubin's speed and breadth could be checked against decades of existing, deep, narrow observations from other instruments. This is also why Cosmos will receive extra observational attention going forward. Because of its value as a heavily cross-referenced, well-understood region, it will be observed more frequently than most other areas in the survey, and Rubin's view of it is expected to grow even deeper over time, revealing fainter galaxies and finer detail than what's visible in this first release. What was published on July 31st is really just the opening chapter of Rubin's relationship with this patch of sky. How scientists will use the data. Alongside the image, Rubin released a full scientific catalog, a structured searchable dataset listing the precise position, brightness, shape, and color of every galaxy and star identified in the observed region. Researchers will use it to study how galaxies grow and change shape over cosmic time, how galaxy clusters and larger structures form, and to refine our understanding of how matter is distributed across the universe, work that feeds directly into Rubin's broader goal of helping pin down the true nature of dark matter and dark energy. One key technique researchers plan to apply is weak gravitational lensing, a subtle effect where the combined gravity of galaxies and dark matter between us and more distant background galaxies slightly bends and distorts the light passing through. Because this distortion is so faint for any single galaxy, scientists need to statistically analyze the shapes of millions of galaxies at once to detect the pattern reliably, which is exactly why a dataset with more than 500,000 galaxies in a single early release is so valuable, especially from a survey expected to eventually chart around 20 billion galaxies total. Because the cosmos field has already been so extensively studied by other telescopes over more than 2 decades, this new Rubin data can immediately be cross-checked against a massive existing body of research, dramatically speeding up how quickly these observations turn into verified scientific conclusions, rather than spending years simply confirming the instrument is trustworthy. Beyond dark matter and dark energy, this catalog is expected to support research into how supermassive black holes grow over billions of years, how galaxies collide and merge over cosmic time, and identifying rare, unusual objects that might otherwise go unnoticed in a smaller survey. Because Rubin will revisit Cosmos more frequently than most other regions, researchers will also be able to track subtle brightness changes over time, potentially catching flaring black holes, exploding supernovae, or other short-lived events unfolding in a region already mapped in extraordinary detail. A human note. There is also a quieter, more personal side to this release. Alongside the scientific announcement, Bob Blum, one of Rubin Observatory's leaders, acknowledged the severe storms that recently struck Chile's Coquimbo region, the same area surrounding Cerro Pachón. In his statement, Blum noted that the observatory's thoughts were with its staff and the broader local community affected by the damage, and he dedicated this particular Cosmos field image marking the true beginning of Rubin's scientific mission to the people of Coquimbo as a gesture of gratitude for the community's decades of support toward astronomy and the observatory itself. It's a reminder that behind even the most advanced scientific instrument ever built, there's a real community living and working alongside it, and that the people who supported this project on the ground, long before any scientific image was published, are very much part of the story too, not just the engineers and astronomers whose names appear in headlines. It's easy to overlook amid a press release focused on galaxy counts and camera specs, but it says something about how this milestone was marked not purely as a technical achievement, disconnected from the people and place around it. The takeaway. So what's the real takeaway here? Not that Rubin uncovered some singular shocking secret in deep space, but something arguably more important for astronomy. Going forward using real collected data rather than test observations, Rubin proved its entire pipeline works is designed from capturing raw light with the largest camera ever built through processing, stacking, and cataloging all the way to releasing that data to the global scientific community on one of the most demanding and heavily scrutinized test cases available anywhere in the sky. 500,000 galaxies cataloged and released, covering just one small corner of a survey that will eventually stretch across a sixth of the entire visible sky and beyond, all captured before the observatory's primary 10-year mission had even ramped up to its regular nightly pace. If this is what a single early data preview looks like, built from less than a year of accumulated validation observations, it's hard to overstate what 9 more years of continuous full-speed observation will eventually reveal about the structure, history, and ongoing evolution of the universe. This is also just the first in what officials describe as an ongoing series of scheduled data previews and annual releases planned throughout the survey. EDP2 builds on an earlier, smaller preview. And it will eventually be followed by the observatories. First full official data release expected once enough of the 10-year survey has been completed to support large-scale, statistically robust studies. Each successive release is expected to cover progressively larger areas of sky, incorporate more observations of each region, and reveal fainter, more distant objects than the one before, gradually building toward a complete, continuously updating 10-year time-lapse of the entire visible southern sky, built from roughly 800 visits to every region observed. Every night from here forward, Rubin will keep capturing roughly 700 new images, steadily working through its list of sky regions and circling back to revisit each one throughout the decade ahead. Somewhere within that constant stream of images, among galaxies already photographed hundreds of times, there's a real chance the observatory eventually catches something nobody has ever properly documented. A supernova exploding in real time, a previously unknown asteroid tracing a new path through our solar system, or some entirely unexpected event that simply has been witnessed in the recorded history of human astronomy. That's the promise behind building a telescope designed not to look once, but to keep watching patiently, night after night for an entire decade, gradually turning isolated snapshots into something closer to a living record of the universe as it actually changes and evolves in front of us. If you want to keep following every major update from this observatory over the next 10 years, hit subscribe. Now, releases like this. Cosmos Field Catalog are almost certainly going to become a regular event, each one adding another piece to the largest astronomical data set ever assembled. Drop a comment, and let me know what stood out most to you. The 500,000 galaxies already cataloged in a single early release, the fact that scientists deliberately tested this new machine against one of the most well-studied patches of sky before trusting it. Anywhere else, the sheer scale of a 10-year survey that will revisit every part of the visible sky roughly 800 times, or the small human gesture of dedicating this milestone to a community recovering from real storm damage on the ground. Thanks for watching all the way through. See you in the next one.